Hi everyone again. Welcome back to the C++ Day 2020. I'm here with Mattia. Hi Mattia.
Hi everybody. Hi
How are you
everybody.
doing today?
Fine,
Have
fine.
you attended the conference so far? Have you enjoyed it?
Yeah, really nice one as usual. I've joined
Okay, then.
the morning talks and so on. Really amazing. Also the Unreal Engine one.
Okay, great. I'll pay you later for saying this. Okay, Matti, we are going to talk about interoperable AI today. So I think we can start. It's something that we have worked together on in the last, I think, 8 months now,
Yep.
and we are still working on it a lot, and we are very happy to share this part of this journey with the community. So let's go. Let's start, and okay, this should be fine now.
Yes. Okay. So let's go. Yes, my name is M.Verasani and I'm working with Marco, and we're glad to give you this talk to you today. And yeah, so the talk is basically on ONNX and ONNXRuntime in C++. And we start with an introduction about these two tools, really interesting tools. So just to give a brief introduction about that, today all the machine learning and deep learning applications are exploding. You can use machine learning algorithms or deep learning algorithms for whatever application you want. And we are really lucky because there are tons of training frameworks or frameworks that you can exploit to build your own deep learning or machine learning algorithms, from PyTorch to TensorFlow, scikit-learn, and so on. So we are really lucky about that. And at the same time, we, with the deep learning application and the machine learning application, algorithms are becoming really affordable also for being deployed on cheap devices like phones and so on. So the deployment targets right now for this kind of application are becoming really big. So you have tons of possibility that you can exploit. So you want to make them run on your own laptop. Maybe you want to make them run on a server. You want them running on an iPhone or an Android device. So possibilities are really infinite, let's say. But there is kind of a bit of an issue about that, because you can the offer, let's say, is overwhelming. So maybe you want to exploit PyTorch, but then you need to find the right tools to deploy your algorithms for a server rather than a mobile phone, and so on. And we find out that sometimes, even if you're working in a company and so on, not all the people knows the same tools. So maybe you have people that they would like to deploy, they would like to make their own deep learning or machine learning algorithms with PyTorch or rather TensorFlow or MATLAB and so on. So we found out this really cool tool, which is called ONNX, which is giving us the possibility to finally have interoperability between all these kind of frameworks. And at the same time, it can target several platforms, hardware platforms, in which you can deploy your machine learning or deep learning algorithms. And the thing's really cool about that, I'm going to give you a brief example. So you are developing your machine learning or deep learning algorithms in PyTorch, for example, but you want to target an iPhone because you want your machine learning or deep learning algorithm to run inside your app that you are making for an iPhone or an Apple device. So the cool thing about that is you know that CoreML, which is the framework that Apple has deployed that you would like to exploit for your iPhone device, maybe you're not that familiar with it to train your own algorithm, so you prefer PyTorch. So a cool thing that you can do is, I'm developing all my algorithms inside PyTorch, then I export them in the ONNX format, and then I can exploit ONNX in a sense that as far as I'm converting my PyTorch algorithm to ONNX, then I can convert it to ONNX to the CoreML framework. And then I can deploy my algorithms inside my application that I've developed for an Apple device. So this thing is really cool because maybe you are not familiar with PyTorch Mobile, or there are issues to deploy directly PyTorch model inside an iPhone, and you know that CoreML is working really good. This is really amazing because you can exploit different frameworks and having like a translator for you that gives you the possibility to pass from PyTorch, go to ONNX, then switch to CoreML, and then deploy your algorithm for your iPhone. And at the same time, it gives you the possibility to, for example, if you're working with a colleague of yours that maybe it prefers TensorFlow rather than PyTorch, and you're working mainly on PyTorch, this gives also the possibility to exchange the models between each other without having one learning the frameworks that the other guys prefer. So it's really, really cool tool. And the community working on it to making it better and have the possibility to keep the pace with all the operators that the deep learning and the machine learning community in the research environment are creating and so on. The community is really big, and it's working really heavily to have ONNX at the same pace of the most famous training framework, like for deep learning, like PyTorch, TensorFlow, and so on. And at the same time, being able to be compatible with all these kind of frameworks. And as you can see, also, a lot of companies are supporting this tool. Also, the big ones like NVIDIA, you can see Sony, and MathWorks, as we say before, because MATLAB you can convert model in ONNX. So a lot of companies are supporting this open source project. But the real cool thing about ONNX is that Microsoft also provided ONNXRuntime, the ONNXRuntime tool. What does it mean? So basically, ONNX is creating computational static graph. So every time you have a computational static graph, that is representing your deep learning or machine learning algorithm. But then when you need to deploy it, you know that you're going into the production phase, and usually from the training phase, you're going to the inference phase. And most of the time, what you do is that when you're going in production, you want to create your own inference engine. So for example, from Python, you tend to convert all your code in C++ to be more reliable and to be able to leverage all the custom accelerators that can make your model even faster and portable. But not everybody is able to create a proper inference engine in C++, and you need tons of people to do that and so on. So Microsoft provided to you this ONNXRuntime tool, which is basically an inference engine that it's exploiting the ONNX, is taking as an input the ONNX model, the ONNX format model, and then it is able to leverage custom accelerators of disparate platform from GPUs to CPUs to accelerate even further your model during the inference stage when you are in production, environment. So this is how it works. So basically, as we say before, it takes as an input an ONNX model, and it put in memory all the computational static graph, and then it basically start to partitioning a bit the graph. So it's creating some subgraph. In this way, part of the graph are going to given as an input to the execution provider to leverage runtime and custom accelerators of different devices like GPUs, CPUs, and so on. So basically, the real cool thing about ONNXRuntime is that you don't have to build your own inference engine in C++, care about which kind of accelerator you need to use for a particular device that you are targeting, but basically is abstracting to you all these kind of custom accelerators and runtimes that this abstraction is called execution provider in the ONNXRuntime terminology, and is giving to you the possibility to leverage them without coding how to leverage this kind of custom accelerators. So it is really cool because it can targeting tons of hardware platforms, tons of them, so from GPUs to CPUs and so on. And the only things that you have to do is maybe just create your own inference session, exploit ONNXRuntime engine, and then it's going to make, let's say, the hard work for you directly. And it is really really amazing tool because, for example, you can have in your organization, you can have some data scientists exploiting whatever framework they want. For for example, TensorFlow, PyTorch, MATLAB, and so on. They convert their model in the ONNX format, and then through ONNXRuntime engine, you can make a global and unique inference platform in which you can run your model in the inference stage and then put in production all this kind of model. And you give freedom to all data scientists and all these guys to exploit whatever training framework they want. And we are going to give you just a brief example of how it works, or how the whole pipeline, you can build the whole pipeline. So basically, you have some data, you want to fit your model to a certain type of data. So what you do, you exploit in PyTorch to develop your own deep learning algorithms or machine learning algorithms. So you process your data, you train your model architecture to fit this kind of data. Then you convert your PyTorch model in the ONNX format, and then you give the ONNX model as an input to your own ONNXRuntime inference engine. And the real cool thing is that you can exploit different platforms, as we said before, different operating system, and you can code it in different programming language. So for example, if you want to target Android devices, you can exploit ONNXRuntime and put it exploiting Java to write your program for the Android devices, or maybe you prefer to exploit C++, or maybe you want to still remain in the Python domain, so you exploit in Python, so you call the ONNXRuntime inside Python, and then you can, at the same time, as we said before, leverage different kind of accelerators that we see in the slide, so GPUs, CPUs, and so on. So this is a bit how it works, and all the ONNXRuntime software that we are presenting to you today. And we are going to give you also some information about the performances. Why? Because if you go to their pages, they are saying that the performances are really astonishing. So they can really outperform a lot of frameworks that are out in the open source community and so on. And we actually have tested it to be sure that everything was through and so on. And you see now these two kind of graphs. And we have run a random forest machine learning algorithm on the Iris dataset, and a MobileNet V2 SSD Lite on one image. And all these kind of algorithms, we have targeted the CPU mainly. Because we know that with GPU, we know that these kind of algorithms are going really fast, but we would like to see, okay, what is happening in a CPU? How they are working on a CPU during the inference. So on the left, you see the random forest algorithm. So we build the random forest algorithm with scikit-learn, and then we have compared the inference by exploiting scikit-learn and the inference by exploiting ONNXRuntime. And as you can see for the graphs, we had a X20 improvement on the performances by exploiting ONNXRuntime. So really huge one. At the same time, with a deep learning algorithm for object detection, that usually object detection algorithms are quite heavy to run. So they take tons of milliseconds sometimes. And we will say, okay, let's see what is happening also with this kind of deep learning algorithms. And the cool thing is that we have compared the PyTorch standard inference with the ONNXRuntime inference. And as you can see, also there, we had a X8 improvement on performances, always targeting an Intel i7 Core i7 CPU. So we went from 35 millisecond to 50 millisecond. So really huge improvement also for a deep learning kind of algorithm on a CPU to do inference. So their statement is true, and really they can really improve the inference performances of your algorithm by leveraging all the custom accelerators that the hardware platform that you are targeting is providing. And now I'm going to give you the word to Marco for the C++ part.
Thanks, Matti. No, thanks for the intro. And I would like to ask the people attending if they have any questions so far. So if you have any questions, please drop them into the Q&A tab in Remo. We give you a few moments if you have any questions on this part, on the introduction that Mattia gave. Don't be shy. And if not, we go through some C++ code. And okay, I don't see questions, so maybe we can follow them at the end if there are any. Okay, so thanks, Matti, for the intro. So it's actually I approached the machine learning world basically 1 year ago, and you know, I studied at the university. I had a few courses on machine learning and artificial intelligence 10 years ago, and then I re-entered this world 1 year ago, and obviously everything was kind of changed, let's say. And so for me, it was quite impressive to have this ONNX project ongoing, because it was important, in my opinion, to have a project trying to do this kind of operation, this kind of interoperability between frameworks. I heard during the years, you know, TensorFlow, PyTorch, MATLAB, and other tools to create machine learning and also deep learning models, but I was wondering how to make them together and also to let people use any frameworks they want instead of sticking with one. So what we did with Mattia in the last year, actually it started before me, probably 2 years ago, and we worked a lot on trying and using in production these kind of things. Before that, we worked on benchmarking these kind of things, as Mattia showed you. And at the end, he will mention that something has been published with the collaboration with the University of Modena. But what I would like to dig into is now some C++ code. So how to run ONNX models in C++. So let me share my screen. Okay, I just check if you. Okay, I have checked that we have one question on Remo. So let me just take it. I paste it into the chat here for Mattia, and also I create a banner for all of you to appreciate this and to read the question. So did you experience some conversion issues, like models not behaving in the same way when translated? And this is from Walter, that I take the opportunity to say hello to Walter.
Yeah, so actually some conversion issues is for now we did not experience that much. It really depends also on the framework that you are exploiting. This we have to say that, because we have seen that with PyTorch everything is quite good, so we didn't have like issues during the conversion. So basically I can give you an example. So if you think about MobileNet v2 is exploiting ReLU 6 as a nonlinear activation. And basically what you're doing in ONNX is exploiting a kind of a clipping operator from 0 to 6, which is emulating the ReLU 6 kind of behavior. And we did not see kind of a conversion issues about that. When a conversion issue could happen is, for example, with a not non-supported kind of translation. So, for example, if I recall correctly, with TensorFlow, sometimes you can have issues in converting a model from TensorFlow to ONNX and maybe see not that good behavior. But with PyTorch, for now, the only issues is that we have experienced, and also with MATLAB, the only issues we have experienced was when the operator was not supported by ONNX itself. So I give you an example. The formable convolutional operator were not supported, like I think 3 or maybe 5 months ago. So what is happening? ONNX cannot convert them. The operator is not existing in the ONNX format, and at the same time, it's not existing in ONNXRuntime format. So this is the main issue. This is the main situation. Maybe you see big conversion issues. But otherwise, from our experience, PyTorch and MATLAB, everything was okay if the operator was in the ONNX and ONNXRuntime kind of framework. And maybe sometimes with TensorFlow, we have seen this kind of issues. But to be honest with you, we haven't tried that much the TensorFlow to ONNX conversion, just a few times. But with PyTorch and MATLAB, I can guarantee you that we haven't seen this kind of issues coming up a lot, just when the operator was not existing. But the cool thing is that you can create your own custom operator in PyTorch. Then you can create it as the same code that you've written for the custom operator in PyTorch, that usually you're exploiting C or C++ to do that. You can then use it to create the ONNX operator, and the same code you can exploit it to use it to create the ONNXRuntime operator. So yeah, that's it.
Well, it's true that we didn't have so many strange behaviors, but we debugged a lot in many situations. Actually, especially because if you are in PyTorch and in Python, you probably can exploit the power of NumPy and also of PyTorch tensor library itself. With the ONNX C++, you will see in a minute, you don't have so many tools, so you have to use other libraries like Xtensor or PyTorch C++ if you need to manipulate tensor and do some complex operations, or maybe you have your own library. So sometimes to fix all the issues with tensors, you have to do some troubleshooting with the dimensions and stuff like that. So it's true that we didn't have conversion problems, but we spent some time in in little tweaks between the PyTorch and the ONNXRuntime for the manipulation of tensors. But anyway, good. Yeah.
I can just add just a quick thing. You can do, for example, when you do a conversion, you can also do in Python an assert to check that everything is all the numbers and so on are correct. So, and we have done it, as Marco was saying, tons of time, debugging tons of time, and we have seen that we didn't see huge gaps in the translation. Just eventually really small gaps. Of course, it is better to debug and not say, okay, everything has been converted, is fine, and so on. So we were doing all these tricks. But most of the times nowadays, you are really lucky that it's just maybe really small things are changing, but are not that dramatic, as Marco was saying. But debugging is a things to do, actually. Yeah.
Okay, so let's go to the code. So first of all, I would like to mention that sorry if I turn my head, but my main screen is in front of me. So this is the entry point for ONNX. So if you want to explore ONNX project, go to onnx.ai. And you can see also the slide showed by Mattia about all the companies, all the partners of this community project, because actually is a community project. About ONNXRuntime, the entry point is this aka.ms/ONNXRuntime. So if you go here, you have a simple website that allow you to download, to guide you through the library that you want to use, depending on, for example, the operating system you want to develop and you want to target, the API you want to, the programming language you want to use, the architecture you're targeting, and stuff like that. So, for example, in the case of Windows, C++, x64, the website recommends to install a NuGet package. That is something that I did for this demo. Actually, for our use cases in our work, we actually rebuilt the library because we needed to use other providers, so other accelerators like the DNNL, for example, in this case. So you have to build it on your own. But in this case, we can explore this demo with C++ Windows CPU, and then I'll show you that the code is exactly the same for the GPU. The only difference is the library you're going to link. So suppose I have this project that is on GitHub. So you can look inside, and also you can reproduce the code I'm going to run. Actually, this demo was shown before for another meetup. So the demo I'm going to run here is a bit shorter, because in that meetup we had 1.5 hours time. In this case, we have less time. So let me just skip a couple of demos. I'm just going to show you just two. Let me, Matti, I'm muting you just because I heard some noise. So that's I don't know if it's your microphone, but just in case. Okay, so imagine I have this project on ONNXRuntime demo linking. If I show you the NuGet packages I have installed, I have this Microsoft ML on ONNXRuntime that is exactly the same as the one suggested for us in the website I showed you before. And I want to show you just the hello world of ONNXRuntime. The hello world is basically loading a model, maybe inspecting it somehow, and running it. So running the inference with some inputs and retrieving the outputs. So first of all, the first thing you do with ONNXRuntime is you create an environment, this ORT-env, and this is basically the entry point to the underlying API. So you create only one environment for each process. And with the environment, you can do some optional stuff like customizing the log. I just want to show you that here you can do something like, you can customize something about threading. This is something advanced I'm not going to show you, but it's something that you can do. You can manipulate the global thread pool that ONNXRuntime is managing under the hood. And also you can share the same thread pool among different sessions. Okay, you can do something advanced. And this kind of thing is something really new. I mean, that has been introduced in the last, I think, in the last 6 months by the ONNXRuntime team. And then you can customize the logging function. So you can choose a default logging level, and then you can customize the logging function, and you can pass in a state. Maybe I don't know if the font is a bit small, but anyway, I can show you here all the overloads available. Here you have this logging level, the logging function, and then you can pass in your own state that will be passed in again when the log function is executed. This is the classical pattern to pass, through callbacks, a custom state. That's something just I want to mention for you. Then you can create a session. This session represents the inference session, so the inference that you're going to run with this particular model. And you have a couple of ways to load a model. You can pass the path to the model, like in this case, or you can pass the array of bytes to the model. Why? Because actually the ONNX is a protobuf. And maybe you get this protobuf from somewhere else, like from, I don't know, from the cloud or from another source. So instead of having the file somewhere, you want to stream it from another source. So you have another overload taking the byte stream. Then you have some options that I'm going to explain you a bit more later. Then you can use the session for inspecting the model just to get some basic information, like the number of input, the number of output, and you can also get the name of each input and the name of each output. To do that, you have to use an allocator, and because basically the library should know how to allocate a string. And in this case, we can even use a custom allocator, but I have used default allocator provided by the library. Remember that this string should be deallocated at the end. And this is why I have this boilerplate here for closing and for freeing the memory. I haven't mentioned that I'm not going to show you a wrapper on top of ONNXRuntime here. I'm just interested in showing you the raw library. it's very likely that you are going to wrap it somehow. For example, to avoid these kind of things, to avoid managing the stuff like strings this way, you are probably going to wrap it somehow. It's not my target in this particular Hello World. I want to show you the library as it is. And in this case, I'm getting the shape of an input. So the shape is the dimension. So the dimension of the tensor related to this particular input, the input in the position 0. This is a very, very simple model. It's a linear regression with only one input and one output, okay? And then I'm doing something very important for our network. I'm basically creating the tensor to pass the input to the network. And ONNXRuntime here is very clever because it allows you to avoid copying data. So you can basically take your own sequence of values that can be a vector in this case, can be an array, or can be something else. It's a sequence of floating points. And what you do is you pass this sequence of floating point as just as a reference, as a pointer in this case. And to this create tensor is an API of ONNXRuntime. And this stuff is actually not going to create your data, it's just going to reference it. Here you have a technical detail, is this memory info. Basically, you are going to use the CPU to allocate the tensors. And actually, at the moment, ONNXRuntime only supports allocated tensors in the CPU. But they are flexible enough in the future to support other kind of allocations. In this case, is the CPU is what we can do. I want to give you a hint from, let's say, from the trenches. So from a developer point of view, ONNXRuntime C++ is not so well documented. I mean, you have to figure out some stuff yourself. A suggestion that I feel like giving you is going to the C API underneath. The C API is a bit more documented. So, for example, here, how do I know that this create tensor is not doing a deep copy? Okay, we go inside create tensor. This is a wrapper on top of this create tensor, and this is a wrapper on top of this global void API, blah, blah, blah. And we are calling this create tensor with data as value, okay? And we go into the C API. You can check the name on the top right corner. We have the ONNXRuntime C API. So we are going to the C layer now. And you can see that the C layer is a bit more documented than the C++. So go into the C layer and you can check something more about the behavior of this function. And in this function, you can see that, okay, create a tensors with uses buffer, blah, blah, blah. Data is owned by the caller. All release value won't release data. So that's important to know. It's important to know because ONNXRuntime supports also the possibility to allocate data. And it's the case for the output in our example. I show you. In this with this call, we are running the inference session. So we are running the model to get the outputs, and the outputs are allocated. So the values are allocated by ONNXRuntime. We don't have to deallocate them because they are deallocated automatically by the runtime itself. Just a couple of details here. You have some run options. For example, you can override the log level for this particular run if you need, and a couple of other options that you can find into the run options. I don't want to go into the details here. But one detail that is really important, you can customize which outputs to take. So if your model has many outputs, you can do a partial output retrieval. In this case, we only have one input and one output. How to do it? How to do that? You have to pass the names. So first of all, you pass the array of the inputs in the order you choose, and then you pass the array of the outputs you want to retrieve, okay? In this case, we only have one output and one input. So at the end, the output values is a vector. I show you the type here is a vector of this particular type ort value. And these ort value are exactly the same tensors that we have allocated before, the same type. And these types actually contains the data. And we can access the data through this function, get tensor mutable data. We have to specify the type, because this is kind of type erased. This is kind of type erased. So we have to state which is the type we are expecting. In this case, we know it's a float. We can, since this is an ORT value, we can also access other properties of this ORT value, like the shape, the number of elements, and stuff like that. So finally, we can then print the values to the standard output like this. So this is the result of the demo. Very, very easy, very, very simple. Probably not so useful now. Just to show you the library. Let me check if you have any questions. If you have some questions about this, it's quite easy. You know, you have just to be careful with some details, like this allocation of stuff, and you have to be careful of the allocation also of the tensors. And also, obviously, you can pre-allocate your output, and you can tell ONNXRuntime to put the output values into your own buffer, okay, for any reasons you want. If you have any questions, please drop them now in the Q&A. Otherwise, I go on, and I can show you something that actually is very, very similar. I have another demo project. I won't run it because actually I have just 15 minutes maybe now. I have exactly the same code here, exactly the same code I showed you for, so since it's still the linear model, but this time I'm linking another library, and I have installed another NuGet package. This NuGet package is called Microsoft ML ONNXRuntime GPU. And this is basically the default choice you have on Windows for running ONNX runtime against the CPU as the first choice, obviously. So the code is exactly the same. The only exception is that you add an execution provider, that is this abstraction ONNXRuntime has to represent different accelerators. So different libraries, for example, you want to use to accelerate your models, like cuDNN or DNNL by Intel and these kind of things. So you basically use this. In this case, you use this function to add a new execution provider that is linking the cuDNN libraries. And then the rest of the code is exactly the same. The only difference is that this code will run the model against this GPU. So by using CUDA. And that's exactly the same. You have to install a particular version of cuDNN in this case if you want to run it yourself. Because when I built this, the version was V7, the version 7, just for your information. If you need anything, just let me know. Drop me an email or open an issue on GitHub, and I will be happy to help you. Now, if you don't have any questions, let me check the Q&A. I think we don't have any questions so far, but I can quickly go through another demo. Actually, we have two demos here. We have two vision networks. One is ResNet, this is a classifier, and one is a detector called MobileNet. I want just to show you this MobileNet. I don't want to go into the details of the network itself. We have some pre-processing and some post-processing that is not so trivial. This code has been done by adapting from code developed by our friends at the University of Modena. So we have a mention here. They are working on a great library called CppDay20. And so they have a bunch of networks, and they have a bunch of code to do pre-processing and post-processing of networks and deep learning models. What I want to show you is, okay, we have this demo. The code is very similar to what I showed you before, but I want to just to give you the result of this, just to show you what this is really doing. So, oops. Basically, we are taking some images from my disk, like this, and we're going to detect some predefined classes on these images with this network, and the output is showed here. So, like, this is a bear, this is a stop sign with a truck in the background. We have a person with skis, we have a bus, and stuff like that. I think you got it. We have a bird, we have a dog with a person with an airplane, stuff like that. So we have a bunch of code to do this kind of things. That's not my point. My point is, suppose I want to fine tune this network. In particular, I want to fine tune the execution of these with ONNXRuntime, and I want to, for example, I want to dig into some details like the profile of this network, how long does it take, and stuff like that. So what I want to show you is ONNXRuntime has some a predefined, very simple but effective for many scenarios profiler that you can configure in these session options. So when you create your session, you can actually profile your session every time it runs by adding here a name, and this is actually going to produce for me a JSON in a standard format, in a tracing format, in a standard tracing format file. This one. That you can open with Chrome, like this one. In Chrome, you have this tool. Probably I have to zoom a bit. Maybe it's better for you now. And then you can drag and drop this into Chrome, and you have some information here. First of all, you can see the time spent of ONNXRuntime in the different phases, like the session initialization. Let me show you a bit more. This is the model loading, and we can see that the model loading was 10 milliseconds. Then we have the initialization of the session that took more or less 200 milliseconds, and then we have the images we recognized. Each image is more or less this order of magnitude. We have 82, 71, etc. And what is very interesting for you here is also the explosion of this execution into its components. For example, we know that this model is using a sequential executor, meaning that the graph itself has not been solved in a parallel way, but has been solved sequentially. That can be an interesting information for you if you're doing your profiling. And also you have a bunch of information underneath that are the explosion. It's the explosion of all the operators in your graph that has been executed. Like, for example, the convolutional operator. This is a MobileNet has a lot of convolutional operators underneath. And you know also that this stuff has been run against the CPU, not the GPU or not another provider. So this is also a double check for you if you're trying to check if this kind of things is running on another accelerator. So what you can do here is you can use this tool to profile a bit your network, your execution. And one thing it's worth mentioning is this time for initializing the model. In this case, it's more or less 200 milliseconds. Why? Basically, because ONNXRuntime, as Mattia mentioned, is doing a graph optimization underneath when it runs, and this graph optimization is executed when the model is loaded. I can try to disable also this optimization to show you the effect. For example, I do disable all optimizations, and I want to show you the result of disabling all the optimization on the graph. And probably you have already felt a bit the time that is longer than before. In this case, we have these, 300 milliseconds now each execution. So this stuff is huge, let's say. And now you don't have this time here. You have 45 milliseconds to open this model. So you can ask, how can I get both, let's say, the advantages, so optimization and also maybe a cheaper loading time? You can do it. You can do it because you can actually save an optimized version of this model. You can save an optimized version of this model. ONNXRuntime can do it for you. And now we have this optimized MB that I can copy here, and I can use it. Oh, sorry, I have saved the wrong model, because now the model is not optimizing anything. So I just do it again. So I can save again this optimized model. Okay, now it's giving me an error. Well, not an error, it's a warning. It's saying, well, I'm going to optimize the model, and I'm going to optimize it using all the available options. Some options won't be portable to other targets. So you are warned about that. That's okay for us. You can play with the optimizations level with this enum here. Okay, you can choose other kind of optimizations that will be portable. And this optimized model now has this is now, yes. Yes, because I haven't copied it well. Sorry. Well, to be sure, let me copy this as path. Okay. Okay. Now I want to show you the result in terms of optimizations here. Okay, as you see here now, the wall duration was exactly the same as without optimizations, so 40 milliseconds, but we have a good trend of all the execution of the images. I have something else to show you. Actually, I don't have so much time. What I can do it for you is I can show you what it means to have parallel execution, but okay, I have a very easy parallel for each that I want to show you the effect of having parallel execution from my code. In this case, the bunch of images have been processed very quickly. But if we see the single executions within any thread, the execution takes a lot of time compared to the execution of sequential images. Why? Because actually there is a contention, let's say, in the global thread pool of stuff. So in this case, okay, the overall effect is that all the bunch of my images have been processed very quickly, but each execution is longer, way longer than before. Okay, you can use this tool, this profiling tool, to also refine these kind of things, to check what is going on, how much time it takes to run a single image or a single network, a single input of your data in your particular model. And also you can see the explosion of all the operators executing, like in this case, all these kind of things for each image. I don't want to go over time. I think I show you everything I wanted to show you. So I'm happy with this. In the demo, you will find also, if you're interested, a simpler network ResNet. This is a classifier. And in this code here, I'm showing also how to integrate XTensor. That is a library to manipulate tensors, very, very similar, let's say, to NumPy. I mean, the objective, the target of XTensor is to be as simple as NumPy for Python developers. And in this case, I'm using it to exploit, especially in the pre-processing of the images. I'm doing a couple of things with XTensor. So if you want to play with it, also I'm using OpenCV for the processing of the images, as in MobileNet. I don't want to steal more time. Just one thing to mention that I forgot to mention before. Matti, if you can please step one exactly. Actually, I have divided the features of ONNXRuntime in three difficulty categories, in my opinion. We have the basic level, everything. I showed you everything in this category. Basically, how to create a session, how to inspect the model, so getting input names, input count, shapes, and stuff like that. How to create a tensor in CPU, because at the moment ONNXRuntime only supports a CPU tensors creation, and how to run the inference, also giving you a bit of feeling about the partial outputs. The custom logger is quite easy. You add it to the environment, but it's something a bit more complicated than the first column. So in the second column, you have other features like the profiler that I show you, and also the graph optimization. We went through a bit of examples. And also we didn't talk about the execution providers, but ONNXRuntime is built around this concept of execution provider. It's very flexible. You can create your own interface of execution provider and for your accelerators, or you have a bunch of execution providers already for you in the library on GitHub. And also advanced features like the custom operators Mattia was mentioning before. So you can create your own operators if they are not supported by ONNX yet, or if they are your own operators that are not, let's say, public. Also, you can play with memory. You can play with memory arenas. You can play with allocators. Many advanced stuff to do, fine-tuned inference, since we are in C++ and also in C. Obviously, you have the same interface, and you have a good support for threading. So that's something a bit more advanced. I didn't want to show you. So Matti, please, I think you can go on. Okay, the demo are in the slides. I will send you all the links. Also, Mattia had great examples for Python. So if you want to take a look. Okay, Matti, please, you can mention. I think you're okay with the microphone now. Yes. No, I cannot hear you. That's strange. Yes, yes, it's fine now.
Okay,
Thanks.
now you can hear me? Okay, perfect. Sorry. So yes, as Marco was saying, there are a bunch of them also in Python if you want to check the export phase from whatever framework to ONNX and then run a simple ONNX runtime thing. And then, as Marco was saying before, we have done a great collaboration with the guys from Unimore, the HyperT laboratory. And we have basically done a research project based on object detection algorithm, one stage object detection algorithm that are working really well for embedded system, because the two stage you need also to exploit data movement, which can be quite, that data movement is taking sometimes every time. So one stage detector are the perfect spot for embedded devices. We have done a benchmark against FPGA, GPUs, and CPUs to see which are the platform it is better for certain kind of operation and so on. And we exploit like Xavier devices from NVIDIA, Silencer for FPGA, and standard Intel Core i7 for as a CPUs. We have done this benchmark with YOLO v3, CenterNet, and MobileNet v2 SSD Lite, as Marco, I showed you the example before. And you can find more information on this paper that we made with them.
Yes,
so
I want to paste the link. Okay, maybe I can do afterwards. Okay, we have, I think, a couple of minutes, because then we go to the closing message that it's still in this track, but we have a couple of minutes. So first question: Can you train a model with ONNX or only run one? Yes, you can train. There is a beta support for training. Matti, I haven't used it. Maybe Matti,
No.
you have some. No, okay.
Didn't try yet.
But there is a support for training as well, only in Python, as far as I know. Another question is, given your experience with ONNXRuntime and its maturity, would you consider using it in production? Well, we are kind of doing it. It's the performances are quite interesting, and so I think it can be a good fit for production. It really depends on what you mean on production. Sorry if I say in these terms, but I mean, probably in some critical scenarios, maybe I cannot tell you if this is usable or not, because I don't have the feeling on that. But we are using it for in the testing phase, and we are going also into production phase. It's something that has been developed for maybe 3 years now, so it's kind of major. I don't know, Matti, if you have some more insights on this, but I think it's also used in many projects now. So
yeah, Microsoft is exploiting it a lot. For example, for BERT inside Bing. So it's exploiting ONNXRuntime.
Yeah, also underneath it's Windows ML, everything is. So I mean, the Windows machine learning platform, let's say, underneath it's with ONNXRuntime. So I think it's mature enough. Should be mature enough. Also, we have many contacts, let's say, using it. So maybe we can take it offline, let's say. So I think we are out of time, but we can follow up in Remo afterwards. We have the closing message now, just in a couple of minutes, still in this track. Closing message is really 5 minutes, and then we can follow up everything in the networking track. So thanks a lot for watching the talk. Thanks for attending, and thanks, Matti. See you in 2 minutes, still here for the closing message. Thanks a lot.
See you. Bye.